Polynomials are one of the most common types of expressions or even equations that we use in mathematics. They look in this form, a in x to the power of n plus a in minus 1 x to the power of n minus 1 plus n minus 2 x to the n minus 2 all the way on down to a2 x squared plus a1 x to the 1 plus a0x0. Now, the exponents on the variables are natural numbers. Or 0. So that really makes them whole numbers. But the idea that they're just these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, never decimal numbers and not negative numbers. Now, 0 is a little bit weirder because when you have x to the 0 power, we get just equal to 1, right? Anything to the 0 power is 1. And so this last term, a naught x to the 0, that just becomes 1. And a naught times 1 is just a naught or a 0. This is a constant term. That's the reason why I said it's natural numbers typically, because this is x to the 1. The x to the 0 power just goes away. It's just 1, so it goes away. And this final term here is called the constant term. It's just a naught. It's just some number. a n minus 1, a n minus 2, all the way on down to a naught. These are coefficients. And really, these are just going to be real numbers that you're going to plug in, any real number that you want. Now, the highest degree is right here. That's what it's called. It's called the degree. And it's always the highest power on the x variable. So we tend to write it at the first, and then the next highest power we're going to write next, the next highest power. That's how we like to write these types of expressions. Always the degree first. The coefficient an, which of course is this coefficient in front of the highest power of x, this is called the leading coefficient. Now, the standard form of a polynomial is written from highest power to lowest power. So if you look at this polynomial here, the highest power is 5. That means that this is a degree 5 polynomial. We're going to write that one first. Then the next highest power is 2. So we're going to write that one next. And then finally, the x comes into play. Even though 890 is the highest coefficient, the coefficient is not what we base the polynomial on. We base the highest power. There's a lot of reasons for this. The highest power actually really dictates a lot of the behavior of the polynomial, not the highest coefficient. So that's why we always write the highest power first. Now, polynomials have different names depending on what kind of thing we're talking about. Single term polynomials like this, where we have 677 x to the 15, there's no other term in there. There's no x to the 14 or 13 or 12 or all the way down to 0. This is called a monomial. Think of mono as one or singular. And so it's a singular term polynomial. The degree, of course, is the highest power of x. Well, there's only one power here, so that has to be the degree. It's degree 15. And the leading coefficient is the coefficient in front of the highest power of x. And there's only one coefficient here, so it has to be 677. Okay, if we have two terms, think of what word will we use for two terms? That's going to be called a binomial. So this one has two terms, negative 18.6 and then negative 45x 13. The degree of this thing is 13. That's the highest power of x. And the leading coefficient is the number in front of that term. So x to the 13 is the highest power. Therefore, negative 45 is the leading coefficient. This, of course, is not written in standard form. We would write this as negative 45 x to the 13 minus 18.6. That is in standard form. But even if it's not written in standard form, the degree is still 13, no matter how you look at it. and the leading coefficient is still negative 45. Okay, if we have three terms, well, if we have monomial, binomial, then three term is a trinomial, such as x squared plus 5x plus 6. This is written in standard form. Highest power is 2, then 1, then 0. This is the constant term. The degree is the highest power, so 2. And the leading coefficient is the number in front of that. There's no number written, but you can always add a 1 in there. So the leading coefficient is 1. Now, anything larger than or I should say anything that has more terms than a monomial, binomial, or trinomial, we typically just call it a polynomial in general. Poly means many, nomial means number, so many number expression. But we still find the degree in the leading coefficient the same way. Now, for adding and subtracting polynomials, it's quite simple. All you want to do is get rid of the parentheses by distributing if you need to. So for these first set of parentheses, we can just get rid of them because there's nothing in front of them, so they don't actually need to be there. This first polynomial is a 4th degree polynomial with leading coefficient 4. Now to get rid of this next set of parentheses, we're going to distribute the negative into each term. And this is a cubic polynomial. The highest power is 3, and the leading coefficient is 16. Now distributing that negative, we're going to get this. And finally, the 15, well, that's just there on the end. Okay, now that all the parentheses are gone, we can combine like terms as you always want to do. So start with the highest power. For this polynomial, this is now a single polynomial. The highest power is 4. There's no other 4s in there, so I'm just going to write that down. The next highest power is 3. That's one right there, one right there. Combining those, we have negative 15.5 minus 16. That's going to be negative 31.5 y cubed. The next highest power is y squared. There's only one of those, so we can go ahead, write that one down. Oh, actually, there's a y squared here. I forgot that one. So we can combine those two now. Let's see, 27 plus 10y, that's going to be 37y squared. All right, the next one is y. We have two of those. Let's combine those. It's going to be negative 1002y. And finally, we have the constants, 103 and 15. That's going to give us 118. So this is a 4th degree polynomial. The leading coefficient is 4 still. 4th degree with the leading coefficient of 4. And this is written in standard form. So that's really all there is to adding and subtracting polynomials. Get rid of the parentheses, combine like terms. Give it a try in number 1. Now, multiplication of polynomials is done by distributing. This is an important idea that I want you to understand. Now, the FOIL method, if you've heard of the FOIL method before, first, outer, inner, last, this is just a special instance of multiplication of polynomials. In this case, the FOIL method works for a binomial times a binomial. The first is going to be a times c, the outer is going to be a times d, the inner is going to be b times c, and the last is going to be b times d. All I've done here is distributed everything in the first polynomial, a into c and d, and then b into c and d. So that's all I've done is just distributive. FOIL method only works, however, for binomials. That of course gives me AC times AD, BC times BD. Now, distributing in general, right? You can think of it like this. We can think of as A distributed into everything in the last. So A is multiplying C plus D. And then you multiply B into everything in the last. So plus B times C plus D. Of course, at this point, we have to distribute it again. A times C, A times D, B times C, B times D. And that's what gives us the exact same thing. So this is the method I want you to think about, because this works for everything, for every combination of polynomials you could have. It more than just binomial. So for this first one here, we have a monomial times a, just a polynomial. It's got 4 terms in it. So to do this, we're going to distribute the first polynomial into everything in the second. So that, and that one. Now, when you're multiplying, you're going to multiply the coefficients together. So for the first one, we're going to go 3.5. Let me show this like this. 3.5 times 4 is going to be 14. Then we're going to multiply the relevant bases together. We have m to the 5th times m cubed. Those are like bases that are multiplying. So we're going to add the exponents. 5 plus 3 is 8. N cubed is, there's no other n cubed here, so we're just going to add it on to the end. Okay, and that's the first term done. Now let's work on the second one. 3.5 times 2 is going to be 7. M to the 5th times m squared, multiplying like bases. Add the exponents. 5 plus 2 is 7. Now we have n cubed times n. N is the same thing as n to the 1 power. 3 plus 1 is 4. Okay. The next one is going to be 3.5 times 6. That's going to be 7 times 3, so 21. That's going to be negative 21. M to the 5th times m to the 1 power. Add the exponents. 5 plus 1 is 6. N3 times N2, it's going to be n to the 5th power. 3 plus 2 is 5. Okay, final one. 3.5 times 10, it's going to be negative, it's negative 10, not just 10. Negative 35. There's no other base with m here, so we're just going to add m first because m comes alphabetically first. And then n cubed times n cubed is n to the 6th power. 3 plus 3 is 6. Now, combining like terms, the variable part has to be the exact same, right? So here we're looking at m to the 8, m to the 7, m to the 6, m to the 5. All the m's are different, so there are no like terms here. This is the best I can do. Now, this technically really isn't a polynomial because we have 2 different variables, and I had only shown a polynomial with 1 variable. You can think of this like a polynomial in 2 variables if you want. The way that you would order this, I would tend to always have the alphabetically first variables, in this case m. I would count down from powers of m. So 8, 7, 6, 5. In here goes 3, 4, 5, 6. So I don't count down from n. I count down from m instead. But that's just my preference here. It's kind of hard to also say what's the degree or the leading coefficient. You could say the degree is the powers added. So this would be like 11, 11, 11, and 11. You could say the degree is 11. All right, moving on. We have a binomial times a trinomial. Now, of course, FOIL method does not work here, but distributing does. So let's distribute 19.25a times 6a times 5b and times by 1. So I can write it like this instead, if it helps you understand what I'm doing. 6a plus 5b plus 1 minus b times 6a plus 5b plus 1. And then we just distribute this into the first one. That's what I was showing up here. It's the exact same thing I'm going to do here. So 19.25 times 6 is 115.5. A times a is a squared. Then we get 19.25 times 5 is 96.25. A times b. And then 19.25 times a times 1 is just 19.25 a. Now we can do b distributed into there. Also up here, that's the same thing as just taking b and distributing into each. Same idea. Negative b times 6a is negative 6ab. Negative b times positive 5b is negative 5b squared. And then negative b times 1 is negative b. Okay, here we do have like terms. This one and this one. We can combine those two. And how do you order this down? Well, it's kind of difficult because here we have both a terms and b terms. I don't know if there's a very good way of ordering it. So I'm just going to write it like this. That was just 115. Then I'm going to combine these like terms here. That's going to give me 90.25 AB. Then I'm just going to write 19.25A minus 5B squared minus B and leave it like that. All right, for this next polynomial, or these multiplying polynomials, I should say, 3x plus 5y, do not make this mistake. This does not equal 3x squared plus 5y squared. Many students make this mistake. This is not true. Don't do this. Instead, this thing equals 3x plus 5y times 3x plus 5y. That's what squared means, right? If I had 14 ABC squared, this is the same thing as 14 ABC times 14 ABC. That's the meaning of the square, or any power. You multiply it by itself that many times, in this case 2. So we're going to multiply 3x plus 5y by itself, multiply by itself 2 times. And here I can distribute 3x into both things. 3x times 3x is 9x squared. 3x times 5 is 15xy. 5y times 3x is 15xy. And 5y times 5y is 25y squared. I have like terms here. Combine those. And I get 30xy. And that is my answer. If you were to solve this one, you're going to see that you're going to get 9x squared plus 25y squared. And you can see we're actually missing a term. That's the reason why they're not equal. All right, give it a try in number 2.